Okay, good morning, good afternoon, and welcome. Today we are going to go through alpha alkylation. And for the bridge assignment, some of these went well, some of these went not well, and most of them were in between somewhere. My goal for this was to see how well we could do of going back to old information and building toward our new reaction today. Our reaction today is brand new, but none of the individual steps in it are new. They're all old stuff that we're recombining and repackaging in a new way. So it is a new reaction. So don't feel bad if you got lost somewhere in the middle of that bridge assignment, because many people did, and it was a lot of different information from a lot of different times over the course of this year. So we're gonna go through it together, but keep in mind that this bridge assignment is the new reaction for today. So we'll, in class today, we'll go through some examples of it. We'll talk about a little different ways that it can be changed around slightly, talk about the bases and why we use LDA instead of anything else. And at the end of class, if we have time, we'll talk about how it fits into retrosynthesis and carbon-carbon bond formation. But by and large, this is the reaction. So if you got to the end and everything made sense, then you got it. And if it didn't, then we'll work through it. And hopefully by the end of the next 15 minutes or so, this will make sense and you'll see how we get there. All right, so we're gonna start at the beginning. This is LDA. LDA is different from LAH. Both of them are 3-letter initials, and both of them are used pretty consistently in this class. LAH, which is lithium aluminum hydride, is an H-. It's a fiercely strong hydrogen nucleophile. This is different. So please do keep them separate in your mind. LDA is what? Let's start off here. It's a negative charge. Since mid last semester, we have seen negative charges constantly, and they fit into one of two categories. They're either nucleophiles or bases or both, right? That's something you remember because it's something we've talked about every week for the last? Yes, that's correct. They're either nucleophiles or bases or both. So this one is a very bulky one. What does that mean? It's just a base. It can't be a nucleophile. It's too crowded to be a nucleophile. So this one is a strong base. All right. Furthermore, in terms of the word strong, we just finished talking about acids and bases. N- is really, 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 really reactive. It's a super, 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 super strong base. The pKb for it would be 14 minus 35, so negative 21, which is ridiculously low. This is a fiercely, fervently, incredibly strong base. Sound fair? Everybody good with that? That makes sense? Okay. That's what we used LDA for in the past. It was one of our bulky bases for elimination. We're going to use it for this as well. But it's a base. That's what it does. All right, so coming on down here, what do bases react with? Don't think too hard. What do bases react with? It's 4 letters. It starts with A. Acids. Bases react with acids, right? Bases and acids react together. Nucleophiles react with what? Electrophiles, and acids react with bases. Everybody good? Okay, so this is not, again, we're not making up new things today. A lot of this is just based on stuff we've done already. So this is a very strong base. I'll just put a little negative charge out there. And it is going to pull off the most acidic hydrogen that it can find. Well, in this case, I didn't give you a lot of options. This is the alpha carbon that's right next to a carbon. What's the pKa of an alpha carbon? Someone knows. It's the most acidic of our CHs. It is 20, yes. So that's about 20. All right, so in terms of your acids, it's not a strong acid. In fact, it's a pretty weak acid. However, remember, we have a ridiculously strong base. All right, so bases, I've made you guys draw the acid-base mechanism many, many, many times. Please keep doing it. It's still the same thing. Your base shares electrons with the acidic hydrogen, making a new bond to the acidic hydrogen. You can't make 2 bonds to a hydrogen, so the electrons that were holding on that hydrogen turn into a new lone pair on whatever is left behind, on whatever your acid was. So we should get a C double bond O next to a C with a lone pair. What's the charge on a C with a lone pair? Negative. Yes, perfect. All right. The other thing you would get is that LDA would be protonated. The LDA is not really something that we care about at this point. It just served its duty already. Now it's protonated. However, this is the other side of the acid-base reaction. What's the pKa of an NH? So an N plus would be 10. What about a neutral nitrogen? Way higher than that. 35, yes. So just looking at this acid-base reaction, would this favor, I know I'm skipping down to number 3, would this favor the products or the reactants? So this should look a lot like your quiz on Wednesday. You've got an acid and a base in a reactant and an acid and a base in the product. We're comparing the strength of our acids. Which one is a stronger acid, 35 or 20? 20, right? The lower number is a stronger. So this is a stronger acid by about 10 to the 15th. It is a million billion times stronger. So which side would equilibria prefer? The side with the more reactive strong acid or the less reactive, more stable acid? Yeah, less reactive, more stable thing. So this reaction is going to favor the products by a factor of 1 million billion products to every one leftover starting material. So you're not quite at 1 mole per molecule, but it's ridiculous how much more product you would get than reactant. Effectively, this is 100% product, 0% reactant. So I'm going to go ahead and change this to just a straight up arrow pointing towards product, because it is going to favor products by about 100%. All right, so the other thing to look at here is that the reason this CH is more acidic than any other CH that we've seen is because this C- is stabilized through resonance. Resonance, it's been a while, but resonance is how we can show charges being spread out to make a molecule more stable, delocalized, if you will. And what we can move around in resonance structure was and still is lone pairs and pi bonds. This would be our resonance structure. In resonance structures, take a second and look at your structures. If you ever have 5 bonds to a carbon, you've done it wrong. There should only ever be 4 bonds to any carbon. But this would be our resonance structure. So looking at these 2 resonance structures, the one on the right is the one that explains why this even happens. And O- is the reason that this can happen. So an O- is far more stable than a C-. But they both exist simultaneously, and that's how resonance structures work. So looking at those 2 resonance structures, which one is more stable, the one on the left or the right? The right, yeah. Why? Why is an O- more stable than a C-? Yeah, it's far more electronegative by a lot. So that one on the right is far more stable. Okay, so if this one's more stable, which one's more reactive? Yeah, the other one, the one on the left. So that one's more stable. This one would be less stable, so more reactive. All right, following up on that, how is it reactive? How is a C- reactive? We can go back. Remember at the very beginning of this? N-, all minus charges, blah, 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 blah. Right? Still true of a C-? All minus charges have the same reactivities, and there's 2 of them. They are what and what? Base and nucleophiles. I need you all to write this down somewhere. Negative charges are bases and or nucleophiles. I need you to remember that for now, forever, and for always. It's really important in this class. It's not something you're writing down for the first time. It's just really important to remember. All right, so this C- that we have right here is very reactive. It is reactive as one of 2 things. In fact, both. What are they? Read what you just wrote down. Base or a nucleophile, right. So let's start with base. If this thing acts like a base, it'll do what bases do. And what do bases do? Yes, go for it, Timothy. They share electrons with what? Bases react with acids. So it would share electrons with a hydrogen, right? It would grab a hydrogen. That's what bases do. So if this C minus grabbed a hydrogen, what would it turn into? Let's see, with a hydrogen. So effectively, just go backwards. So can that happen? Sure, it would like to do that. But note our pKa's. There are no hydrogens left over for it to grab onto because we've pushed this reaction all the way to product. This is the most stable C minus that we have left over in our pot. Make sense? So it can't act like a base, but if it could, it would. So what else could it react like? No, look at your notes. A negative charge is one of two things. We just wrote it down. Base or nucleophile. So it could be a base, it could be a nucleophile. Everybody good with that? All right, and this thing wouldn't discriminate between the two. It will do whichever one it could. The C minus is really unstable. Either of those would make it more stable. So base or nucleophile. A base is just gonna get us back to where we were. So the nucleophile is the only thing that'll get us anywhere new. Does that make sense? But after this first step, it's just gonna sit there and wait because it is a strong base and it is a strong nucleophile, but at this point it doesn't have anything to react with. So it's just sitting there in your pot waiting for you to add something else. All right, so we are gonna draw this reaction out, just the same first step. This is the same first step that we did above. But instead of talking about what could happen, potentially, let's talk about what would actually happen in a molecule. So LDA is a strong what? Still, it's a lot of repetitions today. Base, yes, it's not a nucleophile, it's too bulky, and it's a negative charge. It is gonna pull a hydrogen off of what? Careful. Off of an alpha carbon. So looking at this molecule, this 3-pentanone, it has 5 different carbons. Chloe, tell me one carbon that it could pull a hydrogen off of. 4, great. How do you know? Exactly, it's an alpha carbon, right? The other one would be number 2. In this case, it wouldn't matter because the molecule is symmetrical. So we wouldn't care whether it pulled a hydrogen off of 2 or 4, but the point is it has to be one of those 2 alpha carbons. It can't be number 1 or number 5. Those are too far away from the carbonyl to have resonance structures. So the pKa of 1 and 5 would be 50. These are not going to be possible places to pull a hydrogen off. So 2 and 4 would have a C minus as a resulting anion that would be stabilized through resonance. 1 and 5 would not. So since it doesn't matter, I'm just going to go ahead and pull it off of number 4 just because it's closest. So your base is going to grab a hydrogen and we'll finish up the mechanism where the electrons would move on over. They were holding on the hydrogen and make a brand new C minus right there. This is the same as everything that we have been doing above. And it's the same first step that all of your reactions for this week will follow. You add a base, it pulls a hydrogen off of the alpha carbon, and now that alpha carbon has a C minus, and now it's reactive. We can draw the resonance structure of this. I'm gonna draw it smaller because it won't really matter. So the resonance structure of this would be an O minus, that C double bond C right there. But again, let's refer back to what we did above. Which of those 2 structures is the most reactive structure? O minus or the C minus? C minus. Everybody good with that? Still true? All right, so this is our most reactive structure. So which one's going to react? The most reactive or the most stable? Most reactive, perfect. All right, we have a name for these things, these kind of intermediates that we make. They're called enolates. I'll tell you why. I don't focus too much on the names, but this name does come up sometimes. So enolate probably sounds a lot like enol for a good reason. This molecule right here with an alkene and an alcohol is an enol. This is something we've seen before. That's not up there. But an enol is an ene and an ol. The deal with enols, whether they tautomerized, all of that good stuff. But this suffix ate, we've used this in phosphate, chlorate, sulfate, et cetera, et cetera. An 8 is telling you that you've got an O minus somewhere. And so this is an enol. And so an enol with an O minus is called an enolate. So we sometimes call this structure in the middle here, it's called an enolate. It's not really a functional group, but that's how those things are referred to. I won't use that term very often because more often than not, we just draw structures. But that's what these things are collectively called. All right, so this one's the most reactive. And once again, how could that C minus react? Base or a nucleophile, right? Negative charges, bases and nucleophiles. All right, so at this point, it's just sitting in that pot waiting for you to add something. So let's say that we add methyl bromide, CH3Br. I'm going to ask you to identify some reactivity again. Yesenia, what is the reactivity of a bromine when it's attached to carbon? Yep, right there. Correct. And the leaving group. Carbons next to leaving groups are always what? Timothy. So leaving groups pull the electrons away, meaning that that carbon wouldn't have enough electrons, so it would love more electrons. So electrophile, yes. So back to day one of this class. We don't have essential outcomes this semester because all of the essential outcomes were the essential outcomes from last semester. So all that stuff about identifying negative charges as nucleophiles, alkyl halides or electrophiles, all that stuff is still true. So maybe refer back to that stuff sometimes. That was what you were kind of asked to do for today. But in terms of a carbon attached to a leaving group, we were reviewing this. It has been a while. Leaving groups are leaving groups. The carbons next door are always electrophiles. But check out what we've got. We've got a nucleophile slash base, and we've got an electrophile. So what works? Nucleophile, electrophile. And at this point, it would just be SN2. Nucleophiles attack electrophiles and kick off their leaving groups. Does that sound familiar? Again, it's been a while, but that is our second step. Our nucleophile attacks our electrophile and kicks off our leaving group. So I know all this stuff is back in there somewhere, and I know that it's been months since we did some of this stuff, but hopefully now that you're seeing it, this makes sense. It's that same reaction that we did a lot of last semester was a lot of SN2 reactions. Nucleophiles attack electrophiles and kick off leaving groups. Does that sound familiar now? Now that we're seeing it again? Okay. So what would our final product look like? Letitia, what would our final product look like here? We've made a new bond between whom and whom? Yeah, we've attached our CH3 at that alpha carbon. So I'll go ahead and label this again. This was our alpha carbon. It became a nucleophile, and then we attached a CH3 to it. So in our final product, we would have all of this stuff, and at the alpha carbon that was the nucleophile, we attached it to a CH3. So these are the two steps of our new reaction for today. You add a strong base that removes the hydrogen from an alpha carbon, which makes your alpha carbon from a CH into a C minus, which is a nucleophile. In the second step, you add an electrophile, and your nucleophile that you just made will react with your new electrophile and make a new bond. And all of this action happens at the alpha carbon. So all of this stuff right here is what's left over from the nucleophile. And that stuff right there is what came from your electrophile. You make a new carbon-carbon bond between a nucleophile that you generated in your first step and an electrophile that you added in the second. We call this, I'm going to scroll up to the top and circle it, alpha alkylation. Because what we have done is we have added an alkyl group at the alpha position. Any questions on this? It's absolutely worth drawing the mechanism for acid base and for your nucleophile electrophile. I'm not grading you on your mechanism, but it's a really good way to make sure you're getting the right product and doing things correctly. Your base shares electrons with the hydrogen. Electrons holding that on go back to the acid and become a negative charge. And then that negative charge is your nucleophile, shares electrons with your electrophile, and makes a new bond. So we basically end up swapping things out. We take off the hydrogen and we replace it with an alkyl group. And it all happens at the alpha carbon. All right, questions on that? So if you didn't make it all the way to the end of that on your own, it's absolutely fine. But does it make sense now? Okay, so we're going to practice this reaction a couple times. The first one is going to look exactly the same. Anybody in Zoom have any questions on this? I'll move that out of the way. No? Okay. So let's do a stop sharing, and we'll just go to a whiteboard. So I'm going to draw out the reactants for you to do the exact same thing, but I'm going to give you a slightly different starting material and a slightly different electrophile. So I'm going to start with that, and I want you to add in step 1, add LDA. Draw the product of this reaction. Don't try to do all of this at once. And then in the second step, add benzyl bromide. So a benzene and then a CH2 and then a Br. I'll give you about, I don't know, 4 minutes to see if you can work your way through here. You should end up doing alpha alkylation to your starting material. Alpha carbon, carbon next to it. So what does that mean? It doesn't have any hydrogen. Okay. Right. This is perfect. Which one's going to be? That is perfect. Be careful that you retain all of your carbons here. All right, so for those of you out there in Zoom whose answers I can't walk around and look at, there are 2 alpha carbons here. So which one are we going to pull a hydrogen off of?
The one with the hydrogen?
Yes, correct. So the only one that has a hydrogen, which would be the one on the right. This is a good way of making sure we only have one product, having only one alpha carbon that has a hydrogen on it. that molecule, which carbon?
Oh.
Yes,
The one with the lead. Correct.
all right, where's your carbon? So that's 5 bonds to that carbon. So it's never in a benzene. It should be a. It's okay. It's, so there you go. Yeah. That's exactly right. Good job. And you counted all your carbons, so you didn't lose it. Does that make sense?
Yeah.
Okay, good. Yes. Yes. All right, lovely. All right, so for those of you out in Zoom or watching this later, do check and make sure you've got all of your carbons. It's really easy to lose a carbon here. But we've got our nucleophile is a benzene ring plus 2 carbons. And so when you pull off the hydrogen from the alpha carbon, you will still have a benzene ring plus 2 carbons. And that second one over there, which was the alpha carbon and still is the alpha carbon, is going to be now your nucleophile. I didn't draw the resonance structure of this. I could, but it turns out that the resonance structure, that enolate, isn't going to be the reactive species anyway. So you can just kind of stop here because this is the one that's going to be your nucleophile. And your nucleophile is going to attack your electrophile, which is the carbon with the leaving group, and kick off the leaving group. So I'm going to go ahead and number these. This is carbon 1, 2, and then I'll just call that one number 3. And so I should have 3 carbons in between my benzene rings in the product. I'm going to redraw my nucleophile exactly how it was. And that was carbon 1 and 2. And so now I should have a carbon number 3 attached. Here's my number 3. That was the one that was the electrophile. And that third one isn't part of the benzene ring. It's got a bond to a benzene ring. So just make sure you keep track of all of your carbons. And this is the new bond that we're making right there. It's between what was the alpha carbon, so what was the nucleophile, and then this carbon number 3 that was our electrophile that's then kind of 2 doors down. It's kind of like a new beta carbon, but that's my new bond there between the chunk here that was my nucleophile and the chunk here that was my electrophile. Questions on that? So do you see kind of what's happening? It's the same thing over and over again. We can modify things, but our base is really strong. And so it's going to give us really 100% nucleophile, which is then going to sit there until you add an electrophile. And it doesn't really matter which electrophile you add. We've had really 2 electrophiles that we've used in this class so far. Last semester, we used alkyl halides. In outcome 5 of this semester, we used ketones and aldehydes. Either one is just an electrophile. And nucleophiles attack electrophiles. So I'm going to give you another example here to try. I'm going to change things up a little bit, but you're still going to do the same first step. And you're still going to do the same second step here, but you're not going to be attacking the electrophile of an alkyl halide. You're going to be attacking the electrophile of an aldehyde. So this should look a lot like what you did earlier this semester. All right. Before we get started, I want to point out that you've got an aldehyde here. Right? LDA pulls hydrogens off of the acid, which is the alpha carbon. How many alpha carbons does this thing have? 1. It's on the right. This is your alpha carbon right there. The hydrogen of an aldehyde is not acidic. It's the CHs of the alpha position that are acidic. So this is your alpha carbon. You should pull one of the hydrogens off of there. All right, go. We've got 4 minutes. Good luck. carbon. So we'll be attacking the carbon. Okay, don't see this. So this was step 1, this is step 2. In between, you've got a step 2, which is an aldehyde. It's okay. Yes. So the nucleophile will be attached to what? Carbon monoxide. Yes. Then there's an oxygen. Well, you don't have carbon. There should be a carbon, then an oxygen. All right, so here's the nucleophile. Great. Where's your electron? Oh, you got it? You got the idea here.
It didn't look like it worked out that way.
Yeah, and then this carbon will be attached to this new nucleophile. Where's your electron?
The carbon or the oxygen.
This
It'd
is
be the
not
carbon.
carbon.
That's what I'm thinking.
It's this. Where in this molecule?
Okay, the carbon.
Yes, that's the one. So your nucleophile, that's the electron.
Yeah.
All right, so midway check-in for my Zoom folks. Our LDA would pull a hydrogen off of that alpha carbon. Giving us a C- right here. And that's my nucleophile. My electrophile in this case is an aldehyde. And an aldehyde, the way that we reacted this a couple weeks ago is still going to be the same way we're going to react it. The oxygen's pulling electrons away from the carbon. So your carbon is an electrophile. So the carbon of a ketone or an aldehyde is always going to be an electrophile. And you can attack it with really strong nucleophiles. Those fiercely strong nucleophiles like Grignard's and LAH is how we attacked it before. Well, it'll also work with this C- as well, because the C- is a C- for the most part. So the nucleophile will attack your electrophile, but you can't have 5 bonds to a carbon. So what do we do at the same time? We're going to kick off a hydrogen? Yeah, you push that double bond up to the O. So it's kind of like your oxygen to your leaving group. Hopefully this looks familiar from 2 weeks ago. This was all of our reactions from outcome 5 started with a nucleophile attacking a carbonyl, pushing electrons up to the O. Does that sound familiar? Okay, so just to count our carbons, we've got, this is our alpha carbon right here. That's where all the business is gonna take place. This outcome, we've got carbon number 1, 2, 3, 4, and then we'll call this one number 5. So in my product here, I will still have my 1, 2, 3, 4 all in a row, because your nucleophile really hasn't structurally changed very much. But now the alpha carbon, which is number 2, is going to have a new bond to this carbon number 5. And that carbon number 5 will still have 2 hydrogens. So we can draw these out if we want to. And it'll also have an O that's now negatively charged. So just to number these, this is our 1, 2, 3, 4. That's our carbon number 5. So all of this stuff came from my nucleophile. And notice that, once again, that new bond is happening from the alpha carbon. And this one carbon with its 2 hydrogens and an oxygen is what came from my electrophile. So the bond right there is the new bond that we made. It's a new bond between the alpha carbon and something else. If you attack a ketone or an aldehyde, you have an oxygen left over. You attack what we did previously, which was an alkyl halide, halogen's gone, so you have nothing left over except for carbons. All right, so this is where we are. So why do you think we need this little step 3 with an acid? Yeah, perfect. We're just protonating that O- and turning it into an OH. That would be your product right there. So we've got something new attached to the alpha carbon. All right, questions on that one? So really what this one and the previous one represent is that the first step is the same. We're adding an incredibly fiercely strong base, which turns our ketone or aldehyde into a nucleophile. And then you can add either of the kind of two electrophiles we have. You can either add an alkyl halide, which will just attach an alkyl group, or you can add a ketone or aldehyde, which attaches a carbon group, but it leaves a leftover OH. And those are our new reactions for today. So we got about 25 minutes left. Let's talk a little bit about your choice in alpha carbon and the base that you use. So let's look at, here's all the bases we used so far today. Or sorry, all of the carbonyls we use. We use this one, and we use this one, and we use this one right here. All right. So the deal with all of those is that they only really give you one choice for an alpha carbon to pull hydrogens away from. This one's our aldehyde that we already used. Aldehydes are great because they only have one alpha carbon, and that's where you're going to remove the hydrogen from. Sometimes you'll have a ketone, and one side of it won't have an alpha carbon with hydrogens. So again, it only leaves you really one choice. That's where you're going to pull a hydrogen off of. That's where you're going to pull a hydrogen off of. Well, this one has two alpha carbons, but why does it not matter? Yeah, it's symmetrical, so it wouldn't matter which one you pull it off of. So these are all great starting ketones or aldehydes to use for alpha alkylation, because it wouldn't matter which alpha you pull it off of. All right, so what about, let's say we start with this molecule. It might look like now I've got an issue. So what's my issue? How many alpha carbons do I have? 2. And are they identical? No. So if we start with this thing and we add LDA, remember that LDA looks like this. It is a fiercely strong fiercely strong base. And you're kind of giving it a choice here. It could pull a hydrogen off of the alpha carbon on the right or off on the left. But let me describe to you a little bit about this thing. It is ridiculously reactive. It'll grab the first hydrogen that it sees, and the easiest thing that it can do. It's completely dictated by kinetics. As fast as it can, it wants to become neutral. So which one do you think it's going to pull a hydrogen off of?
The left,
The left. Why?
because there's less stuff.
Yeah, there's less stuff around it. The quickest and easiest thing for it to snatch a hydrogen off of would be the side on the left. So if you ever have a choice, or you ever have, well, you don't really have the choice. If you give LDA a choice, it will pull a hydrogen off of the most accessible alpha carbon, the easiest alpha carbon to grab. For the same reasons that this is a cruddy nucleophile. It's so crowded that it's actually hard for it to do much of anything. So it'll just do the easiest thing that it can. And it'll do it as fast as it can, and it won't ever go backwards. So it's going to reacts with the most accessible alpha carbon. All right, and so the product that you would get here would be that one, nearly 100%. Sound good? All right, so that's how that's going to work with LDA. Let's recall our pKa values. This was the same thing from the bridge. Your pKa's here, the pKa of this guy is around 20, and the pKa of this is around 35. So remind me, equilibria, is it going to products or reactants or both? Products. It's going to products approximately 100%. This is really meaningful. One of the reasons this is so meaningful is that, just like in that last reaction we did, your starting material is an electrophile, and we're making a nucleophile. So if you had any leftover electrophile, then the nucleophile that you made could react with some leftover electrophile. And if they're in the same pot, you can't control that. But thankfully, LDA is such a ridiculously strong base that it's going to react with all of your electrophile just like that and turn it all into nucleophile. You won't have any of this left over, so you won't have to worry about it. Does that make sense? Okay, because if this went half and half, you'd have half nucleophile, half electrophile. They just react with each other. So that's part of why this needs to go 100% to product, which is why we need such a strong base like LDA. All right, so let's look at a slightly different reaction. If I were to start with this same ketone, and instead I was adding sodium hydroxide. Sodium hydroxide is a strong base. Note that this is not our reaction to do. This is how we do alpha alkylation. It's just like this. So what we've done up to this point with LDA, that's how we do it. This is not going to work. So I'm just prefacing this. This reaction is not going to work the same way. It'll do something, but not what we're looking for. All right, so once again, we have a choice in alpha carbon. But hydroxide is not as fervently basic as LDA. So it's going to have its options here. And what we find is that at least momentarily, it's going to make this one instead. And part of the reason for that has to do with the pKa's. Part of the reason has to do with stability. So let's look at the pKa's here in this reaction if I use hydroxide instead. The pKa of an alpha carbon is still around 20. What's the pKa of water? Yeah, depending on kind of which value you look at. Remember, there's that weird controversy. It's either 14 or it's like 15.5. I think we went with 15.5 or 16 in class. I'm going to put 15.5. Either way, it's less than 20. So which way would this reaction go? Towards products or towards reactants? Yeah, towards reactants. But it's not that big of a difference. The difference here is about a factor of 10 to the fourth. So this one up here gives you one leftover reactant for every 10 to the 15th or million billion products. This one gives you one product for every 10,000 starting materials, which is not that big of a difference. So it does prefer a reactant. It doesn't really go forward, but it does work and you will get some product. So this reaction, this is the reason we don't use this for alpha alkylation, is because if you did this reaction, you would get, let's say, one of these for every 10,000 of those. Well, you've just made a nucleophile. But what do you have a whole lot of left over? Electrophile. And so this guy will go back and react with some unreacted parts of itself. And so it's not going to sit there and wait for you to choose which electrophile to add. It's going to react with itself. So it turns out that this reaction here gives you something completely different. And this reaction here is what we're going to go through on Monday. But this is more, at this point, a cautionary tale. You can't do alpha alkylation the way we've done it above, where we plan out our electrophile if you use sodium hydroxide, because it does something else since it gives you a nucleophile, but also leaves a bunch of leftover electrophile to react with. So let me describe really quickly why it acts with a different alpha carbon. And that all has to do with the resonance structures. So reaction-wise, we've already started ignoring these resonance structures. But in terms of stability, we can't really do that right now because it determines which one we get. So the reason that LDA pulls the hydrogen off of the most accessible spot is because it's just the fastest and easiest thing to do. It turns out that you get a pretty unstable product, but LDA is happy and that's all that matters. And so you're done. You don't get a second choice here. Hydroxide, though, it'll pull a hydrogen off, but then it goes backwards and it goes forward and then it goes backwards and it goes forward and then it goes backwards. So it ends up just being determined by equilibria. It gets to choose, it gets to sample the different alpha carbons and figure out which one's more stable. Well, the which one is more stable is this one, as opposed to the top one. And that's all about the stability of alkenes. Stability of alkenes is something we talked about like last October, so it's been a whole while. Does anybody remember what makes an alkene more stable? It has to do with the number of carbons attached to it. Does that ring a bell? Okay. When we were looking at elimination reactions, where you could get a double bond on the right side or the left side of a halogen, the major product would be the one that's most stable. And the one that's most stable is an alkene with more carbon substituents. So like tri-substituted alkenes were more stable than di-substituted alkenes are more stable than monosubstituted. It's been a while, but it's still true, even though we've forgotten it. But this is a di-substituted alkene, and this is a monosubstituted alkene, because this alkene right here has a carbon on the right and the left, and this alkene right here would only have a carbon on the right. So it turns out that this structure, and therefore this resonance pair, is more stable than the one up there. So your fiercely strong nucleophile doesn't give you the most stable product, it just gives you the quickest product, the easiest product to get. Your more choosy bases would give you the more stable one, which is the other way around, pulling a hydrogen off of the more substituted side. Not because it's easier to do, because that doesn't really matter for it, it's because that's the one that's more stable at the end of the day. Right, so this is something that will matter for us as we move into the new reaction that we're going to cover on Monday. But for what we're doing today with LDA, which is the base that we'll always use for alpha alkylation, you're going to pull a hydrogen off of either the only alpha you have, or given the choice, the less substituted alpha carbon. And then you would proceed from there with your second step. All right, any questions on that? All right, so practice this, but it's going to be the same two steps. First off, we add LDA, pulls a hydrogen off of the alpha carbon, makes a nucleophile. Then you add an electrophile, nucleophile joins with electrophile, and then you're done. Good, good? You should practice? You see it? Okay. All right, so for our last 12 minutes today, I want to kind of give you an overview of how this fits into our carbon-carbon bond formation reactions, which should be helpful for retrosynthesis. What I'm going to do is show you the now 5 reactions we've covered that make carbon-carbon bonds, but we're going to think about them a little bit backwards. So this is going to be fast, and if you recognize all of these reactions right now, great. If you don't, they're all in your notes. We've done them forward before. We're just going to think about them backwards. All right, so you may or may not remember that a couple weeks ago in lab, we talked about that carbon-carbon bond formation reactions are really special and they're really important. I made a big stink about how these were incredible and fantastic and we can make new molecules and make bigger things. It's true. The one that we just covered, alpha alkylation, that's the one that's most primarily used in our bodies to make new carbon-carbon bonds. So it's fantastic. But thinking about these in reverse is a little bit more challenging, much like most of retrosynthesis. So I encourage you guys to, in addition to your functional group interconversion flowchart, it doesn't change the number of carbons, to kind of keep a separate list for carbon-carbon bond formations. And the very first one we did was looking at making a longer alkyne. So I'm not gonna spend a lot of time on this one. We did this one in lab that one day. But we could make a new bond directly next to the alkyne. And we did that by having the end of the alkyne as a nucleophile. And remember, an alkyne had a pretty low pH, and so, or sorry, pretty low pKa, so we could pull the hydrogen off and make that C-. And a C- reacts as a nucleophile. So this should be in your notes from that retrosynthesis thing. And then we would attach it to an electrophile that we could come up with by having a carbon with a leaving group. So your nucleophile would attack your electrophile, and it would make a new carbon-carbon bond next to an alkyne. So that was our reaction 1. We did that one a couple weeks ago in lab. All right, so in outcome 5, we did 2 or 3 kind of new ways of making carbon-carbon bonds, but we didn't really put them into our retrosynthesis. So we'll do that right now. One of them was we could make a relatively longer or larger alcohol, and the new bond that we could make would be this one right here. So in between the carbon with the alcohol and the carbon next door, or the alpha, if you will. The way that we did that was to start off with a ketone or an aldehyde, which is, as we saw today, an electrophile. And what do electrophiles react with? Nucleophiles. So if we wanted to make this 6-carbon chunk, we could have a 2-carbon electrophile plus how many carbons in your nucleophile? 4. Right. Anybody remember what kind of carbon nucleophile will attack a ketone or aldehyde? Moderately strong, fiercely strong. What reacts with ketones and aldehydes? That fiercely strong. And so the answer to that is it needs to be a Grignard or an alkylithium. So your nucleophile could attack your electrophile, kick electrons up. It would make a new carbon-carbon bond. So what all these things have in common is they're going to have a carbon nucleophile and a carbon electrophile, make a new carbon-carbon bond. You would need to just toss in a second step to protonate it, and that's how you can make a new carbon-carbon bond right next to an alcohol. So if you ever want to make an alcohol that's big, you can make it from a ketone or aldehyde and add a Grignard. So we did this reaction forward, but now we're thinking about what we did in reverse. All right, the rest of these are all going to be identical products. So if we wanted to do this guy right here, which is to make a new ketone or aldehyde, we could make that between the carbonyl and the alpha carbon as well. So this is going to look very similar, but instead of starting off with a ketone or an aldehyde, in which case you would turn it into a single bond, we want to leave our double bond O left over. So we could attack an acid chloride. This is the one that slingshots and kicks off the leaving group. Once again, an acid chloride, like all carbonyls, this is an electrophile. And what reacts with electrophiles? Nucleophiles, right? So I can't add my Grignard. So it might look like I could just use this same nucleophile again, but anybody remember why the Grignard won't work in giving you this product? So it will attack, but then what else does it do? Anybody remember? Well, so if this nucleophile attacked this acid chloride, it would give you this product, but you'd still have your fiercely strong nucleophile hanging around, and it would attack again. So the deal was, if you use a Grignard with an acid chloride, it ends up attacking twice. And so you could use that if you wanted to add the same 4-carbon chunk twice. But if you only wanted to add a 4-carbon chunk once, we have to add our weaker carbon nucleophile. Anybody remember what that thing was? Copper something, yes. It's the Gilman, that copper lithium. Yeah. So it's still a carbon nucleophile, it's just a weaker version. So it looks like this, and you needed 2 of those little 4-carbon chunks attached, but that's still, functionally, it's the same thing, it's just a weaker version. And it does that whole slingshot mechanism. Attacks the acid chloride, kicks electrons up, they come back down and kick off the carbon. Okay, our third and final major way to make, from outcome 5, to make a carbon-carbon bond is at this location right here. So this will let you make the same kind of thing, but at a different spot. So in between the beta and the gamma. So why would you need 2 reactions to make the same thing? Well, it kind of depends on which carbon you want to attack. Sometimes it doesn't matter. Sometimes only one of them would work. So if we want to make that spot there, we would start with this enone. You might remember these enone reactions because they had 2 different electrophiles. And if you wanted to add a nucleophile that was fiercely strong, like a Grignard, it would always do that direct attack and it would attack the carbon. So if you added a Grignard to this thing, it wouldn't join onto the beta carbon, it would directly attack that carbonyl and basically do the same thing we've got up here. So what kind of carbonyl would we, or carbon nucleophile would we need instead of Grignard? It's the other one. We wrote it up here already. It's not this one. Yeah, the Gilman once again. All right, but in this case, I've got a 4-carbon electrophile. So if I wanted to make a 6-carbon product, I would only need to add a 2-carbon nucleophile. So Gilman is really good for carbon-carbon bond formation reactions. And it's really useful for 2 different things. One is if you attack an acid chloride, you get a new ketone. And one is if you attack an enone, you get a new ketone. But you make a bond at a different place. So this is 2 plus 4, and this is 4 plus 2, but both of them give you the same thing. All right, so once again, here's your nucleophile. Boop, boop, boop. It's that little 2-carbon chunk. It's going to attack there. And so that's how you would get that new attachment. You'd have 4 carbons from the left side, 2 from the right. So all of these are useful when you're thinking about backwards, how could I make a new carbon-carbon bond? Well, the one that you would choose depends on what functional group you want left over and your proximity to that function. All right, so for today, we did alpha alkylation, which meant that we would be attaching something at the alpha carbon. So glance back real quick and tell me which bond would we be making using today's reaction. So look at your products and see which bond you made. Anybody see it? We can go backwards together. All right, so let's go back to this one. This is our very first one. The new bond that I made was between the alpha carbon and what would now be the beta carbon. All right, that's the first one. Here's the second one. It was between the alpha carbon and then what was the beta carbon. We didn't do any of it here, but we make our alpha carbon into our nucleophile. We would join it onto a brand new beta carbon. So using today's reactions, I make a bond between an alpha carbon and the beta carbon. Yeah. So this is the new bond that we're making today. So noticing that, you can make ketones between the carbonyl and the alpha, or between the alpha and the beta, or between the beta and the gamma. So you kind of just have some choices. When we did this whole thing with alkyne, we didn't have a choice. You could only make the bond between the alkyne and the neighbor. But we have a lot more flexibility when it comes to these reactions, a lot more choices. All right, and the way that we do that is we would have an alpha nucleophile, which we made. So note that you made it from this thing plus LDA. But that's your nucleophile right there. Nuke. And if you just want to add on a 3-carbon chunk, we would add on a 3-carbon electrophile. Bop, bop, bop. And how could this carbon be electrophilic right here? What do we need to have attached? Yeah, leaving group. So it doesn't really matter what the leaving group is, usually some halogen. But your nucleophile attacks your electrophile and kicks off your leaving group. So this right here is the step 2 of what we did today. It lets you make a new carbon-carbon bond between what was your alpha carbon, which we made into a nucleophile, and your electrophile, which then became your beta carbon. This reaction, because it's the reaction for today, is not in your retrosynthesis that I posted earlier this week. So your retrosynthesis from earlier this week, those are going to be the only 4 choices for carbon-carbon bond formation reactions. All right, it is 2 o'clock. Anybody have any questions? All right, as a reminder, we do not have lab next Monday or Tuesday. Please use that time to start working on retrosynthesis. I would highly recommend you work in a group. You can work by yourself, but working in a group is a really good way to talk these out. Retrosynthesis is pretty complicated. That being said, if you work in a group and there's 3 of you and you just say, let's just divide and conquer and each of us do 1 page, then it's just as bad as working by yourself, except that you're just hoping for the best for your partners. Instead, work in a group and talk through each of these problems together. It'll dramatically increase your chances of getting it right. Thanks, and I will see you all next Friday. Those of you in Zoom, I will see you in Monday on class. So we do have class Monday and Friday. We're just not having lab. Thanks. Have a great weekend.